pretty cool to see this happening as it is and to be part of it. Also inspired very much by the two keynotes, who I admire both greatly. So I'm taking a particular lens. I work a lot on place-based, community-engaged, participatory research here in Michigan. You can see the two young Michiganders on the left there. And then also with Malawi, I've been working since 1993, since I had the opportunity to come there as a postdoc. And so I continue to work there with university and extension and farmers, as you'll see in the Southern Africa country. So this is quite a wide range, but as we heard earlier from Barbara, smallholder farmers are feeding much of the world and have similar challenges, whether they're in Michigan or in Malawi. And I feel that this polycultures are really important, and I particularly think we have some new opportunities around soil health. So I'm going to focus in on those aspects. Of course, it takes a village, and there are many people who've supported this work, and I just a shout out to some of them here, particularly long-term USAID support in Africa Rising in Malawi for the last 7 years. We really appreciate that and couldn't do it without all that, both institutional and financial support. Also, please note globalchangescience.org, East Africa Node. This is not my personal lab group. This is my virtual hub of our participatory action research. So if you're interested, particularly in the agroecology in Africa, please check out East Africa Node. So first, a bit of a sobering note. We certainly know there's many challenges, but when I first came to Malawi in 1993 as a postdoc, I was put in charge of helping improve the soils lab. And it seemed to me very severe challenges faced many farmers there. Limited resource, one of the poorest countries on the planet, and variable weather, semi-arid tropics, and but I didn't realize it, but things have actually gotten more challenging. There's certainly new opportunities in terms of markets, in terms of democratization, although it's a struggle. They've been waiting to resolve who's the president for the last 8 months. So that doesn't make the international news, but it's really a struggle on the ground in Malawi. But I want to also point out that although Malawi's been heralded as the new green revolution, the heart of the green revolution, because politicians made it their job to make sure smallholder farmers have access to fertilizers. And certainly since 2008, that has seemed to apparently increase yields. You'll see in the bottom of this slide, if you look at the Food and Agriculture FAO distributed yields, what they report is a sudden increase in yields and a general upward trend in yields. Unfortunately, when we look from space and also from the ground, you'll see that it doesn't really fit these perhaps somewhat politically motivated crop yields that are reported to the Food and Agriculture Organization. So we published in Nature Plants what we tried to call the myth of the Malawi subsidies, but in fact we were only allowed to call it the revisiting the Malawi subsidies. What happened is that first we had to find where agricultural lands are, which are not necessarily easy because these are complex landscapes, a lot of smallholders doing mixed cropping. But when we did that, it's primarily maize because it's one of the most maize dominated landscapes in the planet. And perhaps that's part of what's happening here. Net primary productivity in those maize fields primarily, and a few other crops, but the net primary productivity over time is quite variable, as you can see on the higher graph, and going down. So this is discouraging because we have to remember that you can't have greenness of the maize, so rubisco, the photosynthesis, going down, and at the same time yields going up. That's a basic contradiction. I also have a student, Placid Mpekatula, who went back to the late 80s and 90s where the soil pits were dug, and again by FAO, who's made investments in Africa, and went back and remeasured soil carbon in these places, and areas where intense maize cultivation has gone on has led to declines in soil organic matter. So even though they were at very low levels by 1989, because Malawi's been cultivating land. It's a higher population density than much of Africa. So intensive production's gone on for a long time. But at the same time, it's somehow apparently to some degree gotten worse. So perhaps resilience is at risk due to this soil organic matter decline, and we need to call this out and see how can this be addressed. It's kind of a worst case scenario in that many countries in Africa are facing similar situations as fallows are used less, polycultures are used less. Partly we heard from our Botswana colleague because of government policies who see get big or get out as kind of the way forward, which is extremely disturbing for all those who will have to get out. But it's also disturbing because I think it's putting people at risk, making access to fertilizers not in any way combined with polycultures or with agroecology or building soil organic matter. So this has to be, I hope, highlighted, even though it's a painful reality. So I'm going to talk about a learning lab because I feel that we can't just provide options for Africa. We have to support Africans coming up with their own options and their own ways forward, obviously. So we have this learning lab in Malawi. Also, I'll be talking briefly about our work in Michigan. And the future, I really think, is in the hands of citizens, of farmers in these countries. So, Learning Lab in Malawi. So this has been supported, as I said, by USAID, Africa Rising. It's a collaboration of University of Malawi, the Lilongwe University of Agriculture in Malawi. IATA is our overarching mothership, which is the International Institute for Tropical Agriculture, based out of Nigeria, but international in scope. We have many, many collaborators, extension, many farmers. So the dots are where we've been doing multiple surveys, trying to understand what farmers are doing themselves, their own innovations. We also, being agronomists and agroecologists, we have our own experimentations, but these are all on farm. So we try and understand the conditions that farmers actually face. So we have over 1,000 spots that we're monitoring and about 30 trials, replicated mother trials, and then we have hundreds of farmers' own experiments. So I'll briefly touch on some of our findings. But I want to emphasize that this is a participatory process where we plan together, we do action, and we monitor and observe, and then we reflect and report back and replan. So it's an ongoing process. We've been learning as we go, and I'll try and share a few of those learnings today. So we have these mother trials, which just means that they're replicated at a site and that they have many different experimentation options. And then we have farmer-led baby trials, which is farmers' own experiments that are not replicated except each farmer is a replicate. We also have these surveys, which are now over 1,000 surveys, because we really want to know what regular practices are in addition to experimentation, so that we can kind of grapple with what are the real world problems that farmers are facing. And you can see this is in central Malawi and in southern Malawi. We originally chose sites that represent a range from fairly marginal conditions along dry, hot lakeshore to very mesic, mid-altitude, higher rainfall places. So certain Bayesian regressions that we've been doing, we just published in +1, one set, that found that soil organic matter is indeed very important for high yields, and that striga, a parasitic weed, in many sites is associated with very low yields, and we can't ignore it. We knew it was there. Farmers know it's a problem, but like many scientists, we have our disciplines, and we need to really work closer with farmers to understand how they can control striga, with crop breeders, perhaps with weed scientists. We can't just keep saying this is a problem, we have to actually address it, because it turns out no matter what you do to different interventions such as intercrops or compost, if the striga is there, then you're just in trouble, which is really basically an indicator of soil degradation. So soil health is really important, we feel, and polycultures we know are really important, that this is a symptom of continuous corn production, basically. And the agronomic nitrogen fertilizer efficiencies, which should be around 30, like if you add a kilogram of nitrogen, you should be getting back something like 30 kilograms of grain, because generally there's enough rainfall for maize, and this should be very, these are well-drained soils, mostly alpha soils. In the past, we've seen these types of levels, but now we're down to less than 8, and in fact, many cases 2, just 2 kilograms of grain for every kilogram of fertilizer nitrogen applied, which is we're basically wasting this fertilizer and this very scarce resource, and possibly causing pollution too, because you can't just pour on fertilizer and get no response. This is not working. So although we often say organic matter is important, in this case it's dire. We really have to do something about it. And we know that one of the ways to improve it is through agroforestry. And we have data from long-term trials. I'm showing the grandmother of them all, Rothamsted, on the 176 years now on the top right, which is where a lot of our models come from. But an important one that ran from 1991 to 2007, and I really think we need more of these, is a maize gliricidia. Gliricidia sepium is a leguminous tree that was used as a mixed intercrop. And you can see the plot in front shows us really degraded maize, continuous maize production with or without fertilizer. And then on the left, when you have the trees present, of course they have to be pruned frequently, and farmers really haven't adopted the system. But we do know it works as long as you have the labor to do all that pruning. So we can improve soil carbon. And here's the evidence that was published in Agricultural Ecosystems and Environment that these polycultures can improve in detectable ways carbon and nitrogen efficiencies go up too. And this is, fertilizer doesn't change it, doesn't go higher or lower. It's just really basically a tree effect. And this is important because often agroforestry is seen as a way to improve carbon sequestration and to provide these services, but rarely has this been tested on farmers' conditions under marginal African smallholder farms. So it does, when people say in tropical soil you can't improve carbon, you can actually. And this brings us to a real challenge in that I seem to be full of challenges today, but I do think, and we've heard a little bit about this because we heard about from Valentine that, yeah, but our yields up there. And after all, farmers need the yield for feeding their family. They need yields to be able to pay their mortgages or pay their school fees in Africa. So, and other types of expenses. So farmers are really interested in legumes such as common beans shown on the left. Dry beans everywhere I've worked with dry beans have been very popular. Farmers say they're like meat. They really are tasty and are very much valued. But we know they don't do much for soil health because they're usually a net loss. They're only about 50% nitrogen fixation. They're a fairly small statured plant, except for climbing beans, which only grow in certain places, hot, very cold places. So on the right, we have the agroforestry system that we know improves soil health, but it's not producing any food except for maize with a lot of labor. So it's not giving quite the diversity we need in terms of food sources. So this comes to a plant that I always seem to mention because it is a class of plants that's been overlooked, which are sort of these semi-perennials, such as pigeonpea. But there's other ones. Lab is a vine that grows for multiple years if it's allowed to and ratooned, allowed to harvested, then regrow. There's perennial forms of cowpea, long duration mucunas. So there are a few out there that could be actively cultivated to give us these semi-perennials that both provide food, but they also provide polyculture options that improve soil health. So they're right at a sweet spot in the middle. Unfortunately, pigeonpea in many cases has been bred to be shorter statured. And for those who know me, I don't have any problem with short stature, being under 5 foot. But the thing about it is that the goats then can pull them down. They don't provide fuel wood. You'll see that's something that's valued by farmers. So these really short statured pigeonpea in the end become somewhat pathetic soybeans in that they're short and they don't have this insect tolerance that some soybeans have to some extent. So instead of building on the benefits they're providing in a polyculture, unfortunately, modern crop improvement has, December 2019, ICRSAT was heralding their new early short duration pigeonpea, which may fit fine into a rice wheat system in some parts of the Rajasthan, in northern India, but not necessarily what is needed in Africa. So why, again, do we need these deep root systems? What is unique about Pigeonpea? Well, we know that in the lab, the root exudates make phosphorus more sparingly soluble and move it into an available pool. We know that Pigeonpea are excellent nitrogen fixers. So that's true of many legumes, all but beans, unfortunately, much as I love beans. But unfortunately, we don't have much evidence. What do they do under marginal soil conditions? So can they provide those services in a polyculture or in a rotation system on farmers' fields? And this data just recently published by Gina Garland, Joe Six, and others showed that yes, they can. They are increasing aggregates, and within those microaggregates especially, those are nitrogen and phosphorus enriched. So that's pretty exciting. We do have some data on that these short duration semi-perennial pigeon peas, even when they're grown as a somewhat short duration, and perhaps they would provide even more services they were grown as longer duration. So we can see here some biomass that collected by my intrepid student Tumbu Guerambira, digging hundreds of holes across the landscape to measure these biomass. And she found that around a ton of biomass can be produced by Pigeonpea in a wide range of cropping systems, because they're incorporated by farmers not so much as sole Pigeonpea, although that would be a great agroforestry system if it were rotated with other crops. On the left there, sole Pigeonpea. So that's just like an improved fallow. It's just the bush Pigeonpea grown. You can see over 10 tons of biomass. So this is under on-farm conditions. So it's a phenomenal system. But farmers really aren't interested in growing Pigeonpea this way because it grows slowly at first. So weeds could get in there. Like many perennials, it takes a while to cover the land and suppress weeds. But if it's grown with maize, maize provides that weed suppression, and it provides a crop of grain that's valued. So on the right, there's a farmer preferred system, but it does tend to suppress the Pigeonpea, as you can see, the maize Pigeonpea intercrop. So in the middle, we have what we call the doubled up legume system, which has gotten some traction in some parts of Malawi. Peanuts, which are called groundnuts in much of the world, and Pigeonpea, so two legumes together. So I'll come back to that, but it's quite exciting to see that we can get a lot of Pigeonpea biomass in these mixed systems. And a lot of grain over multiple years. We have to consider, the sole Pigeonpea on the left there. Again, that's why farmers aren't so interested in it, because if you combine the maize with the Pigeonpea on the right, or if you combine soybean and Pigeonpea, groundnut and Pigeonpea over multiple years, you start to see some of the benefits. And these double up legume systems are rotated with maize. So you've got maize, groundnut, Pigeonpea all coming from one crop, for example. And the million-dollar question is, does this improve soil organic matter? Because remember, this is not an agroforestry system as yet. It's not full agroforestry. It's a bush, a lot of leaves, and sometimes a lot of roots, as we saw. But you can see in the bottom right there that still the land cover is not perfect. So there's interest in it, but we don't have 20 years of data, as we did from that agroforestry system with Glycidia. So we've used some crop modeling approaches like APSIM, where it's predicting double up legumes will give us probably the best soil nitrogen gains. So that's exciting, but again, is a crop model. We also know from a wide range of on-farm trials that if we compare an environmental index, so that can be like average yield, or in this case, average calories produced. So it's basically an index of how high your performance potential is. Performance potential would be higher if you had high organic matter, no striga, or if you just did good management. So it's an index that combines both farmer and other management and site characteristics. That's the index on the X. And then on the right, we have the calories produced per technology. You can see a wide range of technologies are working quite well, even sole maize, but this is fertilized maize, and showing the variability on farm. But the legume Pigeonpea system consistently, you can see from the yellow line, is a pretty high performer, whether it's a marginal environment or a high fertility environment. And here's another benefit, one of these co-products from Pigeonpea. I often heard that Pigeonpea fuel was being, stems were being used for fuel wood, for kitchen fires, for cooking. But I really didn't believe it until I saw it from my own eyes. And also farmers always come and collect off our trials after we weigh them the fuel wood from the Pigeonpea. So I started to realize this is a real value to farmers. They feel they grow their own fuel wood. And yet it's often not measured. We just measure soil fertility benefits, maize response. So we need to be thinking about all the co-products from these diverse systems, because that is what is being valued by farmers and others. So we've put together radar charts or spider diagrams. These are one way to see, for example, at one site here, women preferred the Pigeonpea double up legume system shown in the purple, but it doesn't maximize maize yield. It does maize response to fertilizer, which again, nitrogen efficiency in the bottom there is very high, because you're putting a tiny bit of fertilizer only in the maize rotation year. But it's hard to beat a nitrophilic crop like maize if you fertilize it well. Although, as I said, some areas we're not getting the fertilizer efficiency that we saw historically, and this is under good management conditions. We have predicted organic matter changes, we have legume residues. So it's really, I think it's good to think about all the different trade-offs. Continuous maize without any fertilizer in red there is just really not viable, and farmers struggle with that one. But many other systems have different trade-offs. So what are farmers doing? So this is the exciting part of our work, is seeing the types of combinations that farmers are putting together with and without compost and fertilizers. Just focusing on the species, we have Pigeonpea being intercrop with maize, grown continuously. So Pigeonpea maize every year. We have it rotated with maize, groundnut or soybean, cowpea in some drier areas. And we think that these are some of the functions that they're getting. Pest regulation, they talk about Pigeonpea providing some striga reduction, some weed suppression, eventually when it is intercrop with maize. So maize provides early weed control, we think, and then Pigeonpea later. Resource complementarity, right? Because it's fixing a lot of carbon and nitrogen, and as I said, some phosphorus solubilization services for soil building, and the fuel wood and livelihoods. However, if you have a choice, continuous maize is a high grain calorie producer. So it depends whether how much you value these other services, and perhaps what are the income streams available. Market access is high and low depending where you are. Pigeonpea in the south of Malawi is purchased and sent all the way to India. In the north, there's no traders purchasing it, and there's no government market access. So this is something where the enabling environment is really important. Pigeonpea can also be a vegetable. It's valued in certain places. Again, enabling environment, or even just nutritional education, so that people understand that eating green pods can provide a lot of benefits in terms of micronutrients and protein. But these are lower yielding, right, than compared to maize. In these polycultures, we have to always remember that monocultures are of maize can be quite high yielding, but not as many nutritious or providing all the other services. The somewhat traditional system of maize, common bean, and pumpkin, which sometimes called the Three Sisters from the Southwest US, is complemented again by adding a Pigeonpea. Sometimes that's used, the grain is used for eating directly or selling, even for feeding poultry in some places, although livestock are quite rare as yet in Malawi, a very poor place. So you can see how diverse these systems are. So let me just give you another example. Here's what showing them conceptually. We have, just to try and show this double up legume system again, because a lot of times people don't quite get it, because you normally wouldn't see two legumes being intercropped except perhaps in a pasture. But these are quite complementary. The groundnut or peanut possibly is benefiting from some sort of hydraulic lift, because we know that groundnut's very sensitive to not having enough water to move calcium And yet, even in drought situations, we don't see groundnut yields being suppressed by this system. So there may be other services from this shrub, such as hydraulic lift that you see in other shrubby systems. So here it is in real life. You see the pigeonpea as how big it is next to the tropical maize, which is quite tall. Pigeonpea on the left there is a vegetable. Double legume rotation, that is one of the innovations coming out of this work. You can see the peanuts. They're growing very well underneath the shade of the pigeonpea, which will later in the season produce its own grain crop and produces beneficial, it may be also improving the number of beneficials in terms of providing the legume energy drink that generally supports beneficials, but nobody has measured that, and I would love to see some data on that. So here's some of the farmers that we have the privilege to work with in central Malawi, near Dedza here. Hundreds of farmers trying out. Here's a wide range of things that when we went and documented what they had on their farms, some trying up to 3 legumes or maize and 2 legumes, some pigeonpea technologies, and at least 1 legume by almost every farmer. So there's a wide range of variations, intercrops and so on, even in this environment where soil maize has been promoted as a modern way to do agriculture. So I'll go into a little bit into our learning lab in Michigan, because I want to get to some of this, how we see we may be able to support more innovation and more farmer learning through soil monitoring, some new directions in that. First, I want to mention again, long-term experiments. I think these are very important for understanding slow processes, such as soil carbon accrual, also erratic processes, such as pests, and control, biocontrol of pests, which came up earlier. So this was an experiment originally designed by Dr. Harwood, who also helped design the famous long-term organic system at Rodale. That's one of the longest in the US. So basically it allows you to look at a typical continuous corn versus corn, soybean, wheat with 2 corn system, years, because this is typical in some parts of Michigan. Wheat's probably declined since this system was set up. And we do it with and without cover crops. Compost management, organic management are some of the things that are also, so we're looking at both rotational diversity, but also can you support some of the services through integration with livestock, represented here by compost applications. Moderate amounts, 4 megatons every 3rd year is quite moderate compared to many other compost treatments in experiments. We also have some red clover. Just 2 take-homes. One is that rotational diversity does improve active carbon, and it depends on the time of year, but particularly, and this was in a drought year that we made these observations, but we've seen this many times, that generally a corn, soybean, wheat rotation, with or without a cover crop, and it actually supports having a cover crop, having wheat in the rotation, will support active carbon. But compost on its own is also a way to support soil carbon accrual and diversity and active carbon. So we shouldn't forget the diversity that's introduced through compost. And this has consequences, beneficial consequences, because when we look back over some 18 years of this trial, then we find that in really mesic years, in good years, when good rainfall at this site, which is quite well drained and somewhat susceptible to drought, that generally the fertilized treatment is the highest performing. But that switches on the left there, as you can see, this is the x-axis is a indicator of drought. So in a very poor year, we actually see just as good or better production under just compost every 3rd year application. So basically we believe the soil organic matter has been built up over time, and we're starting to see that maize yield as an indicator of productivity in the system is very much benefits from that soil organic matter gain, which comes through this diversity of cover crops or diversity in compost. But what happens in the real world? As I said, it's one site. It's important to have these long-term trials. And one of my life missions is trying to improve the number, trying to bring and support the few that are in Africa, because we need these as we have in the US, such as the one at the LTR, NSF funded at Kellogg Biological Station in Southwest Michigan. Very important for these long-term observations. But we also need to engage with farmers because they have different soil types, they have different objectives. So we've done some monitoring, participatory, in that we're working with farmer learning groups. I've just written this up in Agronomy Journal. If you're interested in participatory approaches in Malawi and Michigan, please check it out. We're trying to see how have farmers, have they been experimenting with a range of things from polycultures, mostly in the form of cover crops, compost, conservation tillage, both no-till and reduced tillage of various sorts. So farmers are trying a range of management practices, and we think this interacts with soil type and location. You have very different options and performance in the northeast of Michigan, where it's cold, wet springs, versus the often hot, dry conditions we face in the Southwest. And we need to look at those interactions and understand them better, I think. If we're going to support farmers trying cocktail mixtures of cover crops, we want to be able to help them see what are benefits. So this is where the final thing I want to leave you with, which is I'm very excited about these new handheld monitors. Even in '93, when I was trying to improve the soils lab in Malawi, I felt that we needed immediate indicators rather than bringing soils back to the lab and then being able to tell someone very specifically about soil carbon for one site. While I knew that carbon varied across fields, that it varied over time, but that takes a long time to see that difference. And I was very concerned that we weren't getting the information back soon enough, or ever, sometimes, to Malawi farmers. And similarly, in Michigan, farmers have bigger fields generally, and really quite variable conditions. So when they talk about they've increased their organic matter, and then they didn't understand why, then they send in samples the next year, it seemed to go down. I assume it's sampling issues, bulk density issues. We know the variability. So what if we could give them immediate feedback? Well, I've tried many different sensors over the years. Many of them are variations on the MOT colorimetric kind of garden type. It's basically 1950s technology. Various variations on that. So unfortunately, it's not very sensitive to phosphorus or carbon, which is so important. And then carbon, of course, tells us something about nitrogen availability. So the most important attributes, it's really not telling us. So I worked on various soil health cards and indicators. Wisconsin's done some nice work on that in the past. But farmers, although they're very interested, they often, we find from our data, they don't actually use those day to day. So what if there were a way through a smart app or through small couple $100 sensor to really take measurements on grids? So luckily, we know that spectra, mid-range infrared spectra, but that's cost thousands of dollars usually to measure. We know that's related to carbon, so that's kind of giving us hope. And then we know the visual range, to some degree, basically carbon is black. So if you could somehow use an algorithm to pull out the color of different other aspects of soil parent material, the iron and other aspects, then maybe you could start to see where your carbon was lower or higher. So there was some biogeochemical basis for handheld reflectometer, basically visual light. And so we're working with RSI. Our science is out of Ann Arbor, private lab, but they're all about open data, which is kind of, again, sort of like this conference. I feel like there's these new models out there that I'm quite excited about. We compared their predicted carbon, so this is from the handheld, from a grid of a 30-acre field we did in Northeast Michigan with one of the farmers that we're working with a lab analysis of active or POXY, permanganate oxidizable carbon. And we found some really interesting things, and that often the same areas that were seen as high by one is also highlighted if we could send it to the lab for analysis. So that was encouraging. So as we go forward, we're thinking more and more about, can we use this we're trying this with over 1,000 farmers in Malawi. That's our next step, to see if could it be a tool for extension educators and farmers. In this case, extension educators went to farm fields. We trained them and sent them out, and they found the farmer and then went and talked with the farmer and went to 3 different fields and made recommendations. And they didn't even go online until later to upload the data. They were able in the field, there often wasn't good connectivity, to at least give an indication if the soil carbon was above or below a threshold. At some various decision points, they were able to make some recommendations about what farmers might do, and also feedback on whether their soil carbon was higher or lower in different parts of their fields. So you can see how this might become an important tool, because, as you know, there's this heterogeneity across fields and by soil depth. That's really phenomenal. These are both examples from Malawi, but you can, I'm sure you have your own experiences of this. And of course, it's changing over time too. So proof is in the pudding. What sort of regressions are we seeing? Well, on the left here, in the y-axis, we have AFSIS, which is soils grid. So it's basically what farmers might use now. It's maps. These are very coarse resolution, so hundreds of meters squared. So you might expect that to be not very closely related to farmers' own soil management and carbon changes. So it's not surprising, although it is kind of surprising the sense that I didn't realize how much it was a smooth product, because you can see that apparently no farm was above about 1.5% carbon. And yet we know from our combustion carbon, which we measured for a couple thousand samples, because you do have to train these reflectometers first. You have to do some soil analyses. But once they're trained, we're finding they're quite robust. And we're getting around 65 and up to 85% if we put texture in regression. So we're starting to see that we could...
5 minutes till the end.
Hello?
Just notifications at 5 minutes till the end.
Okay, very good. I'm finishing up here. So you can see again that we can, that the left, there's no resolution of soil carbon, but if we were the ability to take measurements for farmers and see what they've been able to change, they could find hot spots and low spots on their fields, the lab combustion, but we can't afford to do that. You know, that's a lot of money per each sample, and getting information back and mapping it. But the handheld reflectometer on the right is giving us similar identification of locations with 2% carbon versus 0.5%. So you might in the bottom left there want to do some rehabilitation while you have high spots where you could think about how come those are higher. Is it texture? Is it your polycultures? What's going on? So the bottom line here is that now we have some tools that we can then join in a reflective process with farmers. And there's some apps that look at soil color, which I won't go into here, but LAM-PKS is one of them. So we can move beyond a research tool to really an engagement tool, which I'm very excited about. And I feel that this is where we can go now, that we can support farmers and researchers working together to do their own monitoring. On the left there of their diverse cover crops in Michigan. On the right, trying out different shrubs to rehabilitate soil, and then looking at the different profile of soil in Malawi. So we think that this is key to resilience, is not only having the polyculture options for farmers, but also information so that they can make better informed decisions as they go forward, working together with agricultural advisors, educators, and researchers. So thanks very much. Look forward to any comments, and this has been a great opportunity. Thank you.
Thank you very much, Sieglinde. So one question I'm forwarding from Amélie Godin, who's from UC Davis, but she's posting online. So what is the indicator of drought you mentioned and showed in your slide on LT yield, where it was fertilizer versus compost, or was it environmental index?
It is a drought index of, depends on how many days without rainfall. I can, we're preparing that paper, be happy to send a preprint as we work on that. It's in the literature now, the SPI index.
Question is, what was the primary crop before maize? And is there another crop that might be less nutrient depleting than maize that they could grow instead of maize?
So this is in Malawi?
Yes.
So about 80% of the land is in maize, sometimes intercrop, sometimes not. So it's hard to get people to rotate out of maize. And one way, rotation is really important, we feel, because my paper in PNS showed that rotational diversity in this particular situation is even more important than intercrop diversity in terms of stability of maize yield and so on, partly because it's so degraded and so much continuous maize. But it's hard to get farmers to find anything because it's part of, in fact, they say maize is life, right? It's seen as such an important food security crop. And it's not always sure that you can sell your maize and buy something else. So increasing access to seeds of diverse crops, and input and output access, so increasing market diversity, we think is important. One way forward is this double up legume, so that at least you get 2 crops. You might be willing to give up maize for 1 year and really give your soil a rest and do rotational diversity. And I should mention this is a unimodal system. So basically you just have about 4 months of rainfall and you've got to grow something in that time period. Something like Pigeonpea grows into the dry season, so it gives you a little more diversity over time as well as space. But generally, there's only a few other crops that they grow. Cassava in some particular soil types and certain rainfall areas. Tobacco is an important cash crop, but it's really a maize-dominated system, so it makes it challenging.
Prior to maize, what did they grow for a cereal crop, if anything?
Prior to maize, you mean 300 years ago, prior to the Portuguese coming to the region? It was sorghum, like much of Africa. But sorghum now is only grown for a sweet sugary snack or for brewing, but mostly pearl millet is grown. Not pearl millet, sorry. Finger millet is grown for brewing, but it's, again, as an intercrop, or in the south as way up north, occasionally. But unfortunately, pearl millet's usually often grown with burning. It's pretty destructive. But it's hard, I worked for many years for ICRSA. I still do actually work with them. And their mandate crop is sorghum. So I know many of the arguments why people should grow sorghum instead of maize. But there's reasons why people grow maize, which we could go into, basically having to do with yield potential. Under these particular situations, you can get 3 times the yield in maize. So even if you get a crop failure once in 10 years, maize, it really beats the sorghum in these particular circumstances. So I think it should be part of the diversity, and it would be good if there were, nutritional education so people would understand why sorghum is important, but, or even value added, use of it for brewing and so on. But at the moment, maize really dominates the system. And this is a situation, much of the world, maize has come in and even in India, it's starting to push out a lot of so-called minor crops. Didn't used to be minor. So it's a worldwide phenomenon, one that we need to grapple with in our polyculture community.
Yeah, a bit over time, so just a last quick question and quick answer.
Have you ever used mycorrhizal fungi to improve carbon sequestration?
Yeah, how do you think Pigeonpea is increasing carbon sequestration? In other words, you do it through the plant, not through, because, if you add an inoculum, unless you have the background is completely, like after mine spillage or something. If you have there's mycorrhizal backgrounds, right? So we've looked at mycorrhizal diversity. One of my students he hasn't published that work, but it was actually more diverse in maize Pigeonpea than it was in the natural Miamba woodland. So it does support that, and we think that might be part of how Pigeonpea is improving aggregates. So mycorrhizal plays a role, but the way that you manipulate it is through plant species diversity, in my view. Of course, I'm a plant physiologist originally.
Thank you very much.
Okay, great.
Very inspiring and interesting presentation. So now we are moving to the next presenter.
Okay, thank you very much.